Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is motor connection diagrams. Our objective is to learn to read and interpret motor connection diagrams and determine the electrical relationship of the stator windings using motor connection diagrams. As mentioned in the motor nameplate information lecture, available at the Big Bad Tech channel, motor connection diagrams are pictorial representations of the wiring configurations for different voltages if the motor is dual voltage, or for different speed characteristics in the case of multi-speed consequent pole or multi-speed separate winding motors. This lecture primarily deals with dual voltage motor connection diagrams. However, I'll briefly discuss multi-speed motors before we close up shop. Manufacturers offer dual voltage motors so their products can meet the needs of industrial applications in various countries characterized by different electrical distribution voltages. Long story short, you get 0 points for creativity. Follow motor connection diagrams exactly as illustrated, otherwise serious repercussions may result. As discussed in the electromagnetic interaction lecture, available at the Big Bad Tech channel, the polarity of the magnetic field is dependent upon current direction, and a motor might be damaged or at the very least not work well if it is improperly wired. This fact necessitates a brief note of caution before we begin. Always consult the datasheet for your particular motor. Do not assume the motor connection diagrams and terminal numbers as illustrated in this lecture are universal in nature. A thick, tangled jungle of peculiarities exists, especially for older motors, and it is incumbent upon you to determine the correct connection diagram for the specific motor of interest. Additionally, this lecture operates under the assumption you have a passing familiarity with three-phase AC and Y and delta configurations. Other lectures at the Big Bad Tech channel discuss these topics. Finally, this lecture may take some thought and visualization on your part. Pause the lecture if you need to and get a good feel for these diagrams. Draw pictures, take notes. Let us begin. The 4 common three-phase AC motors: permanent magnet synchronous motors, electrically excited synchronous motors, squirrel cage induction motors, and wound rotor induction motors ordinarily come with 3, 6, 9, or 12 stator leads, where the stator is the stationary part of the motor. Electrically excited synchronous motors and wound rotor induction motors will have electrical connections to the rotor, being the rotating part of the motor. Permanent magnet synchronous motors and squirrel cage induction motors will not have connections to the rotor. We'll largely ignore the rotor this lecture and concentrate our attention on the stator leads. Depending on how you connect the stator leads determines 1, the electrical configuration of the stator, either Y or delta, 2, the resulting voltage and current each stator winding experiences, and 3, the rotational direction of the rotating magnetic field produced by the stator. We'll discuss the rotating magnetic field and introduce reversing motor starters in later lectures. This lecture primarily deals with the first 2 aspects of motor connection diagrams. Let's initiate our discussion about motor connection diagrams with a discussion of 3 and 6 lead motors. These ordinarily represent single winding per phase motors and are meant to be run on a single predetermined voltage, meaning these are ordinarily not dual voltage motors. A 3-lead motor comes pre-wired in a fixed Y or delta configuration. In contrast, a 6-lead motor allows the user to determine if the motor will be connected in either a Y or a delta configuration. A 3-phase AC motor with 3 leads essentially comes pre-assembled in either a Y or a delta configuration and is meant to be operated at a single voltage, and there's really nothing you can do about it. Direct measurement of the current through an individual winding in a 3-lead Y-configured motor is the easiest of tasks. Note, however, the central node of a 3-lead Y-configured motor is ordinarily inaccessible. Voltage measurements of the individual windings, therefore, are problematic and invasive for Y-configured 3-lead motors. Direct measurement of the line-to-line voltage across an individual winding in a 3-lead delta-configured motor is the easiest of tasks. Note, however, since ammeters must be employed in series, current measurements of the individual windings are problematic and invasive for 3-lead delta-configured motors. Determining direct electrical power consumption of 3-lead motors in either Y or delta configurations are therefore problematic. For this reason, some cunning trickery must be employed. Those with an understanding of three-phase AC circuit analysis will realize there exists a relationship between line-to-line voltage and line-to-neutral voltage, as well as line current and winding current for balanced three-phase AC loads that can be employed to our advantage. For balanced three-phase AC electrical loads like motors, line-to-line voltage is square root 3, or 1.73 times as great as line-to-neutral voltage. For balanced three-phase AC electrical loads like motors, line current will be square root 3, or 1.73 times as great as current through a delta-configured winding. This mathematical trickery allows a technician to take easily accessible line-to-line voltage and line current readings external to the motor, regardless if it is Y or delta configured, thereby circumventing invasive and problematic inspection. Lectures on three-phase AC power calculations, available at the Big Bad Tech channel, discuss this cunning trick and more for balanced three-phase AC loads like motors. Note that 3-lead, three-phase AC motors do not offer flexibility. A 3-lead, three-phase AC motor comes pre-assembled as a Y or a delta, and that's that. It is for this reason manufacturers offer 6-lead motors that allow a motor to be configured in either Y or delta configuration depending upon a user's preference. Rather than pre-wiring the motor in a fixed Y or delta configurations, a 6-lead motor allows access to both ends of a single winding. Here I've drawn the A winding with terminals 1 and 4, the B winding with terminals 2 and 5, and the C winding with terminals 3 and 6. If one wanted to place this 6-lead motor into a Y configuration, terminals 4, 5, and 6 are tied together forming a central junction of the Y. Terminals 1, 2, and 3 are left to be connected to the three-phase AC source, where direction of rotation is determined by the phase sequence. Given nodes 4, 5, and 6 forming the central node of the Y are now accessible, a technician has direct access to the voltage across each winding without resorting to any mathematical trickery for power consumption calculations. The motor connection diagram might illustrate a 6-lead Y configuration using a diagram similar to this. If one wanted to place this 6-lead motor in a delta configuration, terminals 4 and 2, terminals 5 and 3, and terminals 6 and 1 are tied together forming a triangular delta configuration, where corners 1, 6, 2, 4, and 3, 5 would be connected to the three-phase AC source, where direction of rotation is determined by the phase sequence. Given both ends of all 3 windings are now accessible for this 6-lead delta configured motor, a technician could directly measure current through each individual winding without resorting to any mathematical trickery, though I will admit this still isn't easy by any means. A motor connection diagram used for a 6-lead delta configured motor might look like this. A quick note about Y and delta configured 6-lead motors before we continue. Recall that line-to-line voltage is always 1.73 higher than line-to-neutral voltage for a 3-phase AC system. Each winding in a 6-lead motor configured as a Y would therefore see less voltage than each winding in a 6-lead motor configured as a delta. This difference between line-to-neutral and line-to-line voltage, in effect, makes a 6-lead motor a dual voltage motor. However, it's not for this reason 6-lead motors are ordinarily employed. The customizable Y or delta nature of 6-lead motors can be used to reduce inrush current in a method called a Y-start, delta-run, reduced voltage starter. We'll return to discuss this topic in greater detail in later lectures. However, as a brief overview, consider a motor starter that starts a motor in the Y configuration and then transitions to the delta configuration after a predetermined length of time or after the motor has come up to a predetermined speed. When started in the Y configuration, each winding receives the smaller line-to-neutral voltage, and voltage, being the cause of current, inrush current will be less. Once the motor has achieved a given speed, counter-electromotive force, sometimes known as CEMF, a concept discussed in the electromagnetic interaction lecture, will be greater, and then full line-to-line voltage can then be applied in a delta configuration. The stage application of voltage to the motor windings ensures inrush current doesn't place an unnecessary burden on the electrical supply system. We'll discuss this and other methods of reducing inrush current in later lectures. Moving on to 9 and 12 lead motors, we find ourselves in true dual voltage motor territory. Regardless if the windings are to be configured in a Y or a delta, the general rule is this: high voltage series, low voltage parallel. When a motor is to be operated at high voltage, the two windings for a particular phase are placed in series with one another. This way, each identical winding drops half the voltage and current would be half as much. When a motor is operated at low voltage, the two windings for a particular phase are placed in parallel with one another. This way, each identical winding drops the same amount of voltage and current would be twice as much. This way, electrical power consumption, being the product of voltage and current, is comparable between motors utilized in either high voltage or low voltage configurations. In the high voltage configuration, voltage is higher, but current is lower. In the low voltage configuration, voltage is lower, but current is higher. This is to suggest that given a choice, the higher voltage, lower current configuration may be preferred given the cost per foot of thicker gauge wire necessary to run the lower voltage configuration. Regardless, the electrical power consumption and the mechanical power delivered should be the same for either configuration. 9-lead motors are essentially an extension of 3-lead motors, in that a technician does not have a choice over Y or delta configurations. These motors typically feature windings pre-wired in a Y or a partial delta. The remaining leads can be wired in series or parallel with the pre-wired Y or partial deltas to allow connection to a high or low voltage source. Consider a 9-lead Y-configured motor. Terminals 7, 8, and 9 form the pre-wired Y with windings A2, B2, and C2. The central node is not ordinarily accessible for a 9-lead motor. Terminals 1 and 4 are the two terminals of coil A1, terminals 2 and 5 are the two terminals of coil B1, terminals 3 and 6 are the two terminals of coil C1. Consider a 9-lead Y-configured motor necessitating a high voltage configuration. In a high voltage configuration, we need to create a series configuration of windings. In this case, terminals 4 and 7, 5 and 8, and 6 and 9 are tied together to form a large Y, with each branch being the series combination of two windings. For this reason, high voltage series Y configurations are sometimes referred to as big Y configurations. Phase voltages L1, L2, and L3 would be applied to terminals 1, 2, and 3. The motor connection diagram might illustrate a 9-lead high voltage Y using a diagram similar to this. Consider a 9-lead Y-configured motor necessitating a low voltage configuration. In a low voltage configuration, we need to create a parallel configuration. In this case, terminals 4, 5, and 6 are tied together to form the central junction of another Y. Then terminals 1 and 7, 2 and 8, and 3 are 9 tied together. Phase voltages L1, L2, and L3 would be applied to terminals 1, 7, 2, 8, and 3, 9. The motor connection diagram might illustrate a 9-lead low voltage configured Y motor using a diagram similar to this. This low voltage parallel configuration is almost like two Y configurations overlaid on top of each other. For this reason, low voltage parallel Y configurations are sometimes referred to as YY configurations. Note, for a truly balanced 3-phase AC load like a motor, you wouldn't ordinarily need to connect the two central junctions. Consider a 9-lead delta configured motor. In this case, the pre-wired windings only partially complete delta configurations. These partial deltas can be placed in series for a high voltage configuration or placed in parallel with one another for a low voltage configuration. Winding A1 has terminals 1 and 4. Windings A2 has terminals 7 and 2. Windings B1 has terminals 2 and 5. Winding B2 has terminals 8 and 3. Winding C1 has terminals 3 and 6. Winding C2 has terminals 9 and 1. Note terminals 1, 2, and 3. A 9-lead delta connected motor does allow access to both ends of an individual winding. However, Note that at each corner, the manufacturer has already tied two windings together. Consider a 9-lead Y-configured motor necessitating a high-voltage configuration. When you wire these windings in series, or a high-voltage configuration, 4 is connected to 7, 5 is connected to 8, and 6 is connected to 9. In this case, it creates a really large delta with each corner to corner from 1 to 2, 2 to 3, and 3 to 1 consisting of two windings in series. This series high voltage configuration is sometimes known as a big delta. Phase voltages L1, L2, and L3 would be applied to terminals 1, 2, and 3, pending desired direction of rotation. The motor connection diagram for a 9-lead high voltage configured delta motor might illustrate this configuration using a diagram similar to this. Consider a 9-lead delta configured motor necessitating a low voltage configuration. The parallel low voltage configuration takes some visualization skills since it's a little busy. In this case, terminals 1, 6, and 7 are connected together, forming the top corner of the parallel delta. Terminals 2, 8, and 4 form the right corner of the delta, and terminals 9, 3, and 5 form the left corner of the delta. When you squeeze the three partial deltas together, winding A1 is placed in parallel to A2, B1 is placed in parallel to B2, and C1 is placed in parallel to C2. You might want to pause the lecture and look at this one. First time someone showed me this, I stared at it for 20 minutes without blinking before I saw what they were talking about. The parallel low voltage configuration is sometimes called a delta-delta connection. Phase voltages L1, L2, and L3 would be applied to terminals 167, 284, and 395. The motor connection diagram illustrating a 9-lead low voltage delta might illustrate this configuration using a diagram similar to this. Moving on, consider a 12-lead 3-phase AC motor. This motor is the most flexible in that it allows a technician to configure it for use with high or low voltage in either Y or delta configuration. In this case, both terminals of 2 windings per phase are accessible for a total of 12 accessible terminations. Winding A1 has terminals 1, 4, winding A2 has terminals 7, 10, winding B1 has terminals 2, 5, winding B2 has terminals 8, 11, winding C1 has terminals 3, 6, and winding C2 has terminals 9, 12. Consider a 12-lead motor necessitating a high voltage Y configuration. Terminals 10, 11, and 12 are tied together, forming the central node of the Y. Terminals 4 and 7 are tied together, placing winding A1 and A2 in series with one another. Terminals 5 and 8 are tied together, placing windings B1 and B2 in series with one another. Finally, terminals 6 and 9 are tied together, placing windings C1 and C2 in series with one another. Phase voltages L1, L2, and L3 would be applied to terminals 1, 2, and 3, where phase sequence determine direction of rotation. The motor connection diagram, illustrating a 12-lead high-voltage Y-configured motor, might illustrate this configuration using a diagram similar to this. Consider a 12-lead motor necessitating a low-voltage Y configuration. The parallel low-voltage configuration forms one Y by tying together terminals 4, 5, and 6. Then another Y is formed by tying together terminals 10, 11, and 12. The two Ys are placed in parallel by tying together terminals 1 and 7, 2 and 8, and 3 and 9. Phase voltages L1, L2, and L3 would be applied to terminals 1, 7, 2, 8, and 3, 9, where phase sequence determine direction of rotation. The motor connection diagram, illustrating a 12-lead low-voltage Y configuration, might use a diagram similar to this. Consider a 12-lead motor necessitating a high-voltage delta configuration. The series high-voltage configuration ties together terminals 4 and 7, placing windings A1 and A2 in series. Terminals 5 and 8 are tied together, placing windings B1 and B2 in series. Then terminals 6 and 9 are tied together, placing windings C1 and C2 in series. Then 1 is joined with 12, forming the top corner of the series delta. 2 is joined with 10, forming the right corner of the series delta. Finally, 3 is joined with 11, forming the left corner of the series delta. Phase voltages L1, L2, and L3 would be applied to terminals 112, 210, and 311, where phase sequence determine direction of rotation. The motor connection diagram illustrating a 12-lead high voltage delta configuration might look something like this. Consider a 12-lead motor necessitating a low voltage delta configuration. The parallel low voltage configuration ties together terminals 1 and 7 and 4 and 10, placing windings A1 and A2 in parallel with each other. Then terminals 2 and 8 and 5 and 11 are tied together, placing windings B1 and B2 in parallel with each other. Then terminals 3 and 9 and 6 and 12 are tied together, placing windings C1 and C2 in parallel with each other. Then the 1-7 group is joined with the 6-12 group, forming the top corner of the parallel delta. Then the 2-8 group is joined with the 4-10 group, forming the right corner of the parallel delta. Finally, the 3-9 group is joined with the 5-11 group, forming the left corner of the parallel delta. Phase voltages L1, L2, and L3 will be applied to group 1-7-6-12, 2-8-4-10, and 3-9-5-11, where phase sequence determines direction of rotation. A motor connection diagram illustrating a 12-lead low voltage delta configuration might look something like this. Let's see if we can put what we just learned to good use. Here's an example of a 6-lead motor. When we open the connection box, a handy cheat sheet pops out written in a number of languages. Even if you don't speak any of these languages, diagrams accompany it. As great as this cheat sheet is, expect it to be lost soon after the motor is installed. That's why motor connection diagrams are ordinarily scribed on the metal motor nameplate affixed to the motor. In this case, the motor has 3 coils, U, V, and W, and each coil has 2 ends, U1 and U2, V1 and V2, and W1 and W2. The terminal block is arranged quite cunningly in that a set of 2 jumpers can be used to connect the motor in either a Y or delta configuration. The 1 and 2 terminals for individual coils are not directly across from each other on the terminal block, but rather diagonally offset from each other. The purpose behind this diagonal offset becomes readily apparent when the jumpers are used to configure this motor in a Y or delta configuration. Note when we compare this cheat sheet to the initial state of the motor, we can see that this motor came shipped in a delta configuration. U2 is connected to V1, V2 is connected to W1, and W2 is connected to U1, forming a triangular delta configuration. The corners U1, W2, V1, U2, and W1, V2 form the connection points to the 3-phase AC source, where direction of rotation is determined by the phase sequence. When we remove all the jumpers and check the resistance of all 3 coils, the ohm meter says that they're all around 42-ish ohms. When we reinstall the jumpers in a delta configuration, note that an ohm meter used to check resistance from either corner sees around 28-ish ohms, which is the series combination of 2 windings of the opposite corner taken in parallel with the corners being inspected. This is a great sanity check. 42 plus 42 is 84. 84 in parallel with 42 is 28. Because this is a balanced 3-phase AC load, 2-point resistance measurements at all 3 combinations would yield the same value. We can rest assured that this motor is properly wired in a delta configuration. Using the cheat sheet, we can now remove the jumpers and reinstall them as recommended to produce a Y configuration. Using the angularly offset terminals, 2 jumpers connect the 3 terminals U2, V2, and W2, forming the central junction of the Y. Terminals U1, V1, and W1 would be used for connection to the 3-phase AC source, where phase sequence determine direction of rotation. Note that an ohm meter used to check resistance from either corner of the Y sees around 84 ohms, which is a series combination of any 2 windings. This is a great sanity check. 42 plus 42 is 84. Because this is a balanced three-phase AC load, 2-point resistance measurements at all three corners would yield the same result. We can rest assured this motor is wired in a Y configuration. That's about it for dual voltage motor connection diagrams. Before we close up shop, however, I'd like to briefly touch upon dual speed motors. As discussed in the rotating magnetic field lecture, changing the number of active pole pairs in the stator changes the rotational speed of the rotating magnetic field, something called synchronous speed. The different configurations used for dual speed motors in effect change the number of pole pairs in the stator via one of two methods. Consequent pole, meaning you get rid of some pole pairs by sending current in the opposite direction, or separate winding, meaning there really are different windings that you can connect or disconnect to change the number of pole pairs per phase. These configurations change resultant speed only and are not related to high or low voltage operation. The reason I'm not spending a lot of time on dual speed motors is because you're most likely not going to run across them unless you're working on really old equipment. Dual speed motors display a marked difference between high and low speed settings and have largely been replaced by a power electronics device known as a motor drive that varies excitation frequency, thereby directly influencing rotational speed. Varying excitation frequency rather than pole pairs per phase allows for finer tuning of rotational speed and necessitates no physical modification to a motor. In conclusion, this lecture discussed motor connection diagrams. We examined generic 3, 6, 9, and 12 lead motor connection diagrams and discussed dual voltage motors, Y and delta configurations, and briefly discussed multi-speed motors using consequent pole and separate winding methods. Additionally, we put our knowledge to practice and examined a motor and its associated motor connection diagram and used an ohm meter to confirm electrical configurations based upon the motor connection diagram. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource and be sure to check out the Big Bad Tech channel for additional resources and updates.